All right, we can begin. Thank you to all those who have joined us. We know it's an especially busy time for students as well as professors. Thus, we truly appreciate the opportunity to be here with you today. Welcome to the FORTHEM European University Alliance Climate and Resources Lab online lecture series on the climate crisis and climate action, which is going to take place here on this platform from today, the 19th of May, until the 3rd of June. The series is more or less a joint effort by the students of the lab, including me from the University of Latvia, Greta and Vivi from the Johannes Gutenberg University Mainz, and Roberta from the University of Palermo. So it brings together students and professors from different European countries and diverse backgrounds. And today is the first lecture in the series of 4 altogether. And the topic of the lecture is going to be climate basics. We will be joined by Dr. Māris Kļaviņš, who is going to speak about what the climate of the Earth is, how it has formed, and what is the greenhouse effect, and Dr. Normunds Stivriņš, who is going to speak about the proxies and methods used to understand the past climate, which can also help to predict future climate change. A few housekeeping rules before we commence. We'll begin with 2 back-to-back, sorry, my internet. We'll begin with 2 back-to-back 30-minute presentations. During the presentations, all of the participants will be muted and the cameras disabled. Once the presenters finish, the Q&A will begin and the microphones will be enabled to those who have questions. So please make sure that your microphone basically is turned off if you're not asking a question, and vice versa to turn it on when you're asking one. And also feel free to write your questions in the chat or just raise your virtual hand during the Q&A to speak up. And on another note, the lecture series will be recorded up until the breakout room session. And the recordings will be posted online once the series finishes. So those who have signed up will receive the link as well. All right, I think we can begin. Māris, I'm giving to you the rights to present right now.
This will be about some very basic questions. What is climate? How it is formed? And what is affecting climate? And it seems that these questions are simple, but actually it is not so, because the people, especially if we are speaking about climate change, very often mix what is weather conditions, and what is the climate. And actually climate is not what we see on every day, as basically climate is result of mathematical calculations. It is a long-term weather regime in a specific territory. So what we see outside now, it is weather conditions. And weather conditions, of course, are much more variable than climate. Just an illustration of major climate zones on the Earth, and we can see desert climate, tropical climate area, boreal environment, and it illustrates relatively stable weather conditions in each of these sectors. And climate in some areas is much more stable than the weather, and it is influenced by solar radiation, large-scale atmospheric circulation processes, and yet once the climate is long-term and averaged atmospheric physical parameters, which are for Earth's overall global climate and to some specific area, regional climate. And actually very many factors are affecting Earth's climate. There are so-called extraterrestrial factors. And at first, of course, major factor is solar radiation. geometry of air-sun circulation, also very different impacts coming from space. And actually, if we are looking on the weather forecast, then it is possible to look also on space weather forecasts, which are influencing climate. And also on Earth, there are many factors which are affecting Earth's climate, for example, volcanic emissions, atmospheric chemistry, and many others. And the human impact is just one of those factors. So the climate is formed, influence is formed as a result of solar energy interaction with the Earth. And so the Earth's climate system consists on major Earth spheres. Most important, of course, atmosphere, but at the same time also biosphere impacts, hydrosphere impacts are of major significance. And it all supports possibilities to model climate system. How the human impact is through different gases which are emitted. And one of the major greenhouse gas, of course, is carbon dioxide. It is coming from very diverse sources, but of growing importance is emissions of methane. And methane, the sources of methane are not only, for example, oil production, but also rice cultivation, cattle cultivation, and similar processes. Also, ozone can be considered as gas belonging to greenhouse gases, and also water vapor. So principally, if the temperature is increasing, evaporation is increasing, then global warming process is self-accelerating. So water vapor is able to absorb infrared radiation very intensively and reflect it back. Nitrogen 1 oxide and some gases which seems to be maybe somehow exotic, chlorofluorocarbons, carbons, the same freons, and also sulfur hexafluoride. Sulfur hexafluoride is a gas which is very intensively used in uranium production, and especially for enrichment of uranium. So, for example, countries like as Iran, also presently, and North Korea is some of very significant emitters of sulfur hexafluoride. In Latvia, the consumption of sulfur hexafluoride, in Latvia, of course, it is not used in nuclear technologies, is just 1.2 kilograms per year. And starting from this year, yet one gas is identified as greenhouse gas. It is also a fluorinated compound. It is nitrogen trifluoride. So all these substances, they are able to trap infrared radiation and return it back on the Earth's surface. And each of these gases do have different ability to drive global warming. And this capacity to influence the global warming can be expressed as radiation quantity, as watts per square meter or calories per square meter. And from this respect, of course, the major greenhouse gas is carbon dioxide. Normal sources of carbon, the normal concentration of carbon dioxide is around 250 to 320 parts per million. It is 0.03% by volume, but presently carbon dioxide concentration has reached 435 ppm. So this increase is really significant. And the natural sources of carbon dioxide is the composition of organic matter, respiration of living organisms, of course, burning of biomass as well as volcanic emissions. And especially the decomposition of organic matter is becoming more and more important. And again, there are direct links between the warming and intensity of the composition of organic matter. And just some examples very close to those which Normunds demonstrated: the changes in areas covered with glaciers, changes of ice-covered, snow-covered areas in mountains, also changes in areas covered by permafrost in northern regions, and in general, of course, most of greenhouse gases are highly stable, and high stability do have freons, especially higher fluorinated freons, do have their half decay time in atmosphere could be more than a few hundred years. Nitrogen 1 oxide is highly stable. Its half removal time from atmosphere is around 120 years. Very stable is also nitrogen trifluoride. Methane relatively is less stable, as well as, of course, carbon dioxide, which with atmospheric precipitations could be eliminated from the atmosphere. And the actual impact can be of different greenhouse gases can be evaluated looking not only the concentrations, not only emissions, but most important is the radiation quantity. How big part of the solar radiation is returned back to the surface, and of course stability. And again, yet once you can see that some freons, especially highly fluorinated, the same nitrogen 1 oxide is highly stable. However, their emissions, especially in case of nitrogen 1 oxide, could be really high, and they can be even compared with amounts of emissions of carbon dioxide. And of course, as a result of this are actually exponential increase, especially if you are looking from historical perspective, from perspective of few hundred years, then the major greenhouse gases, concentrations of them in atmosphere has really increased, and it is a major reason why the climate change are happening, and major activities should be taken to reduce their impact. Three major impact greenhouse gases, their concentrations in last centuries has increased significantly, and it means that also the impact on the Earth's climate is stable, and urgent action should be taken to reduce these impacts, not only to mitigate climate change, to reduce the impact and to reduce the concentrations of greenhouse gases, but also of importance are also maybe could be also so-called geoengineering approaches, and it means trapping of carbon dioxide, safe storage of carbon dioxide, and maybe also other greenhouse gases, but also adaptation. And adaptation strategies is presently one of really important priorities of climate law, which in Latvia is under preparation. Not only mitigation of climate change, but also adaptation and maybe application of carbon capture and storage approaches. Very briefly, just the essence and maybe some questions.
please raise your hand if there are any questions regarding this, as well as the first part. Māris, you can speak, I think.
Yeah. Before everything crashed, among I believe you mentioned 4 factors that affects the former climate. You mentioned also geometric relationships between Earth and the Sun.
Yeah.
How do you think how much of current climate change, how much of the impact is, well, of course they are interconnected, but how much of it could be attributed to perhaps some changes in the wobble of the Earth's axis or solar activity, such factors?
Yeah, so-called Milankovitch cycles, which have had major impact during glaciations, and I suppose it is a topic which is of one of interest also for Normunds. So if you are looking from geological perspectives, then of course the Earth's rotation, Earth's location in respect to Sun has been one of the major factors which has influenced the last glaciations. Actually, it is, these processes are relatively slow, and principally, as much as I remember, some more or less significant impact could start maybe after some 40,000 years. So presently, the percentage of this geometrical profile of Earth's rotation around the Sun could be quite minimal, or we can even neglect it. However, the solar cycles do have shorter timing, and principally the variation of solar radiation intensity could have a bit more significant impact than these periodic processes with very long periodicity.
So the Sun could have been a culprit to attribute some effects of the current climate.
Yeah, and of course also the cosmic radiation. Actually, there have been some hypotheses that the cosmic radiation could have that the changes of cosmic radiation, cosmic rays, could be major reasons of some of the ice ages in the Earth's history. But the more detailed proof of these hypotheses demonstrated that they are not relevant to existing situation.
Thank you.
So my name is Normunds Stivriņš, and without further ado, I would like to continue with my topic today. Well, about the basics of climate as such, you will hear from Māris Kļaviņš, but I would like to dive into the climate reconstructions. So it's no surprise that over the last 100 years, we see that this trend of uprising temperature is still continuous, and well, we expect it will still go further, even warmer. So, but how we know about the climate? So one way is to instrumental measurements. So you can do it by yourself, outdoors or indoors, and or just to see what's the temperature differences every day. And then the next one is paleoclimatology. And this is a term for past, let's say, deeper past temperatures and the climate in general. And the pros and cons. Of course, we have, for the instrumental measurements, we have really precise estimates about actual conditions of the climate. But then for the deeper past, we should apply something else, because with the instrumental measurements we can measure up to 300 years at the best, but then we switch to paleoclimatology, which brings us to millions of years into the deep past about the climate. And these paleoclimatology reconstructions and paleoclimatology are used by major global organizations like IPCC, UN, US, Europe Union as well, and NASA. And they use to evaluate possible scenarios which have been recorded in the past and try to model something to the future. And to reduce model-related uncertainties and produce more reliable estimates of, let's say, 21st century climate and environment, paleo-evaluation techniques are applied to simulations of the past. Yeah, as I mentioned, we try to use something to verify and to be sure that we can predict something to the future. And one way how to do it to make estimates about the past is to look into the vegetation proxies, or in this case, pollen grains. Every year, millions and millions of pollen grains have been emitted to the environment. And the pollen for, let's say, pine is looks in one way, but for the, let's say, lime or alder, they will look differently. So this means that we can say by pollen, if we identify this from, let's say, from the lake sediment, then we can say what kind of plant has been growing in the past. For each plant, there are some thresholds and also limits for the growing factors. So one would be mean air temperature, other would be, let's say, other like precipitations, but in this case, let's take the mean temperature of coldest months and the mean temperature of warmest month, and then we can see that each species or genus is growing in different climatic conditions. Then if we have multiple species or genera in this case, then we just compile on each other this information about the area or the gradient in which species tend to live. And then we find this sweet spot where we have overlap for all species, and that we assume as the average air temperature. So this is really simple way how to explain, of course, but moving further about the paleoclimate and paleoclimate reconstruction. So that was the basic, what we need to understand, that we know the present day climatic conditions under which plants are growing in certain areas and gradients. So to make something to reconstruct, at first we need to go to the lake, then we obtain the sediment. So we basically core the sediment out from the lake. Then we analyze layer by layer the fossil pollen, so basically the pollen grains. As you recall, then we can specify what kind of plant or tree was growing at that time when the sediment was accumulating, and then we can say what temperature was back then. But this we cannot do without modern reference or training set. So we need to know about the modern day pollen composition, and this we obtain from the topmost surface sediment in the lakes, or let's say the first soil sample centimeter, we analyzed pollen grains there. Then we look what's the modern climate at that site, and then we run calibration. So we say, so this composition of pollen grains indicate that the climate is in this range. And then we do some magical mathematical kind of equations, which we are calling or refer as transfer functions. Then apply this transfer function on fossil pollen, and then we got this paleoclimate record. So to obtain past climate from based on pollen grains, we need to at first we need to see what kind of plants have been growing there in the past, and then we need to apply the modern day training set, and then we can kind of run this reconstruction. As we now know, then we need different kind of ingredients to make to reconstruct the climate. Over the world, we have plenty of information about the modern day pollen composition, and one such example is from EMPD version 2. So this is Eurasian Modern Pollen Database, where we have for our continent the modern pollen data. So how it does look. So let's zoom in one site, one of my analyzed sites, which you can find in this pollen database as well. So you can see at the bottom part, we have different Latin names, Picia, Pinus, well, what else? Alnus, Betula, and so on. So these are trees, and for each we have certain pollen percentages. So that means which tree was more in that area and which was less. Yeah, so therefore we can say what kind of environment and what kind of climatic conditions they are. Then when we have this information, well, this is really complicated, the slide, but the idea is really simple, that we need to find some statistical correlation, and we just need to be sure that what we are getting, what kind of results. So on the left side panel, you can see this linear correlation. So what you can see now, we have variable what we would like to reconstruct. So these are taxons, yeah. So some kind of gradient. We have some kind of gradient and some ecological gradient and some variables. So we would like to see some kind of clustering of the certain groups, and indeed we can see this. So as you pay attention here, we have green species here, taxa. Then we see that this taxon is right here. Then reddish, brownish, or orange is right here, and then the violet one. So, and these are 3 taxa. So we see that these variables are specifically in time at certain range. So then we can see that indeed the vegetation have been changing, and thus the most likely also temperature. Yeah, if we know then also the temperature. So, and up to date, we have worldwide available fossil pollen records from all the globe, more densely from Europe, and therefore we have more paleo or pollen-based temperature reconstructions available from this region, as well as North America, and also uprising from China and Asia quite intensively now. And these reconstructions we do use in verification of models, because you need to understand that climate modeling is something different than climate reconstruction, because climate reconstruction, there we apply some evidence like pollen grain from the sediment, and we then reconstruct based on certain evidence, while the modeling involves estimations like usage of equation and algorithms of mathematical equations. Yeah, so that's kind of different approach. For that, we intensively use supercomputers. So this is something different. Yeah. So here now we would like to zoom in into our region. So Latvia is here. So this is northern Europe, and like 25,000 years ago, it was glacier was covering all this area, and some 15,000 years ago, whole territory of Latvia was ice-free, and that means all the sediment in our region, organic, let's say, lakes and bogs and peatland and forests, are not older than 15,000 years. Why I'm showing the lake water? Because all the pollen and plant remains, or any remained trapping into the lake environment, it stays for a long period because there's limited oxygen conditions. So that means a good preservation conditions. Yeah, so there we can find pollen, plant remains, and other remains, if we only know how to get them out there. The basic idea behind this is that we should now again remember this glacier stuff, which melted away 15,000 years ago from Latvia. Then we can see the glaciers melt away. So this is number one. So the lake watershed formed, lake itself formed, then started accumulating different kind of particles, substances. So layer by layer, it accumulated from the glacial melt away up to the industrial times and to the present day, where we can see that the topmost 3 or 2 centimeters represent the present day status. Yeah. Therefore, we can now know that all the sediment are at the bottom. So that means at least 15,000 years. Yeah, but the present is here. In Latvia, we are fortunate to have winter still with the ice formation on the lakes, and therefore last winter we went out and cored openings into the lakes and ponds and collected different kind of material from there. And this we do almost every winter, and we analyze lakes as they are superb environmental objects where we can analyze something continuously and without disturbances. These sediments are mostly undisturbed, so we can be sure that everything what has been accumulating there is on nearly natural conditions, or if the human came there, then we can separate this signal of human from the natural environmental conditions. Well, but let's not to overthink this all, but okay. So when we core, then we need to know at what depth we are coring, where we are coring. Then we see in this case we have been coring at a depth of 17.9 meters deep lake. Yeah, so for that we use different kind of techniques. One technique is well, here we have some video, but it will not work today as a PDF. But you can see a tube, a transparent tube. This we lie down into the topmost sediment, which is a loose or rich with a water saturated sediment, and therefore we need some specific technique how to obtain this loose sediment. And then we can take it out and slice centimeter by centimeter for our purposes. So this is how it looks like. Yeah, so here you can see two examples from man-made water body and the natural large shallow lake water body. And the topmost sediment is here, 2 to 3 centimeters. You see it's a major differences here. The one is rich in sand grains, the other is more rich in organic material, and the water itself, water column, is more turbulent in in this huge dynamic lake than a small man-made quarry. Yeah, it's nice to sometimes also to see how the sediment actually looks like. Then when we have this loose sediment obtained, then we can go deeper in with a organic core. Let's call it in that way, auger, or what's different kind of names in UK and Western Europe. So I'm not sure which one is correct for your region, but the idea is simple. We collect meter by meter the sediment, unmixed. So this is not mixed sediment. We then again can slice centimeter by centimeter this sediment and then analyze in the lab. And then we analyze this for, let's say, 1 to 2 years. We establish a chronology by different kind of techniques, most likely in our region, C14 or radioactive carbon dating we apply. And then we see it's a past and then the present. So, and this is the average summer temperature for the Eastern Latvia based on pollen grains. So we went out, we collected pollen, fossil pollen, then we have information about the modern pollen. We know this composition, and we know also the temperatures in which these plants are growing. Then we are able to reconstruct the past temperature. Well, what we see here is that let's bring up also the present average summer temperature. You can see it's this orange yellow line, and there have been some times in the past when in our region climate during the summer was warmer than today. Of course, today's signal must be also considered, and this is what we are now working on to see whether we already have been above these temperatures or not, because we might be there already beyond this warming. But these studies are in progress. Nevertheless, you can see that the temperature gradient is from 14 to 17 to 18 degrees, so 4 degrees, this kind of jump or increase and decrease. But then when we look the average winter temperatures, you can see it's let's say it's from 14 to even -2 degrees, so it's much more higher kind of interval of gradient for the temperature rise. And the warmest time period, again, based on pollen temperature reconstruction in our region, was 8,200 to 4 to even 3,000 years ago. And this is based on winter. And if you take into account what's going on today, then we see that high Arctic regions are actually increasing in temperatures, and mainly in winter temperature. This has been seen, and the same applies for the past. We see that winter temperature was the most drastic changes, especially in winter temperature. Yeah, so. And this is important and significant point because most, or at least major part of the plants are sensitive to the winter temperature changes. Summers can be short, but again, the total equilibrium of air temperature might be similar. But if we have warm winters, then we don't have snow. And we do know that for the spruce in our region, we need this snow. So for other species, we need this cold weather. And if we don't have, then we see the shifting biomes. And this we might expect also in the future. Yeah, and I have still 5 minutes. Let's bring in some example about abrupt climate change based on our records as well. You see, it's the late glacial, so basically the ice melted away. Then we see the air temperatures started to rise up, but then suddenly for 1,000 years it dropped down by several degrees and then started again rising up. And now is the question, why? Maybe some of you know, some maybe not, but this we called as the Younger Dryas cooling event. And based on latest studies, we see that 12,800 years ago, there was a meteorite hitting into the Greenland, western Greenland. And there have been scientists found already that there's a huge 31-kilometer wide crater beneath the ice sheet. So, and now we think that the concept would be that due to this meteorite crater formation, we see that probably dust form from this impact into the atmosphere, so that sunlight was then reflected, covered. That means lower air temperatures in our region. Then again, this crater impact melted huge amounts of fresh water, which then ran through this Baffin Bay into the North Atlantic Ocean. Warm current, which then shut down the Gulf Stream. And therefore, in our region, we see that at least in Europe, by at least 4 degrees, the temperature dropped in less than 10 years. So it's an enormous change in the climate. And we are really sensitive to this North Atlantic Gulf Stream. If that would not be today, then we probably would not be able to live here, because it would be just too cold and not so good for living here. Based on this cold event, there is the movie Day, the Day After Tomorrow, if someone has seen this. So this is about the same story, not the impact hitting the Earth, but about the shutdown of the Gulf Stream, what might happen one day. Of course, it's the Hollywood movie, but still nice to see that they are sometimes taking something from science to see, to make their movies. The consequences for our region, we analyzed the Baltic countries and published into already 2016 about the consequences. We see that the summer temperatures dropped abruptly at this time. So the time frame is past and closer to the present, 14,000 years, 11,000 years ago. So 12,800 years ago, we see that abrupt decline in air temperature, then increase was not visible for 1,000 years. And during this time, we see that treeless tundra was growing in the Baltic. So that means Arctic alpine vegetation was preserving here, with reindeers and mammoths were inhabiting this region. But then, as you can see, they're stopped here. And this is due to the global warming. So after this Younger Dryas, we see climate improved, and we see that the sun isolation, sun was heating enough, and CO2 was forming enough in the atmosphere, and the climate in general become warmer. And this is previous global warming with 0.17 degrees per decade increase. Today, for your knowledge, we have 0.2 degrees per decade increase in in temperature. So these numbers are comparable. And what we can see due to this last global warming in our region in the Baltics, we see that huge amount of Arctic alpine vegetation and flora and fauna go extinct, mainly due to the reason that we don't have enough good environmental and climatic conditions anymore. So you need to imagine if the climate change, then also other at first vegetation, which is the diet for the animals. If it's changing, then also the animal composition is changing. And if there is no space or no food for them, then of course they will either, well, there are several options, either go extinct, adapt, or let's say migrate, somewhere else. So these three options, but that's a different story. And today about the climate. Well, this is just as the example, what the consequences we can see from our region, based on first of all from the pollen-based temperature reconstructions and up to the even extinction episodes. And we'll see how it will work further. Okay, I think I fit in quite nicely in the time, and thanks to my team, our team, not only mine, but we are all persons, scientists who are working. Of course, this is the core, but we have a quite wide team collaboration network with Helsinki University as well, Tartu, Tallinn Technology University, and so forth. I can't name them all here, but this is what we are doing now, and what we can say about the climate and how we can reconstruct it. Okay, thank you.
All right, thank you, Normunds. So we can start the Q&A session. So if anyone has any questions to Normunds, please raise your hand and I will unmute.
My question was about, as far as I understand, with pollen method in general area of Latvia and in the Baltics and Scandinavia, we can reconstruct the climate only up until the last stage. But that doesn't mean that we can't use this method more closer to equator, yes?
Yes, Māris, you are correct. I mean, well, there are some exceptions for our region. Let's say in Finland, there is site Sokli, which covers also the last interglacial. So that was 130,000 years ago, when it was before the last ice age. We see that there are sediments preserved quite nicely and shows how warm it was at previous interglacial. So there are some exceptions, but these are hidden in some valleys and beneath some other sediments. So but in our region, in Latvia at least, we have not found such sites, treasure sites up to date, but so that means we can analyze up to 15,000 years. But for the whole Northern Europe, we have some exceptions. As regard for the equator, sure, we have really long, extensive kind of period of information about the vegetation and the climate as such in closer to the equator. But then we need to look for proper site from where to analyze. So
I can imagine that in more southern climates, there are lack of such sites.
Well, it depends. I know that in Italia, Italia, the pronunciation is horrible. In Italy, Italia, I don't know what's up to me, but in Italy they have one bog, which is 180 meters thick, if I'm correct. So it was really world record of the peat thickness, and of course they have been analyzing this in high detail. So you might have, let's say in Africa, in those regions where you have deep lakes, you can analyze something. Then you can find even in Sahara Desert, in sites, certain regions, let's say, not pollen, but phytolites, which are forming in between plant cells and forming a sort of opal silica crystals kind of formations, and then we can analyze layer by layer again and to see what kind of plants were growing in the past in Sahara. Because in 5,000 years ago, it was green. It's not like today, the sand. It depends from the aim, what you are looking for, what you would like to answer, and then you just need to know which method to apply, and then from where to find. And for sure, we can find some technique for each continent or each region, which would work in most of the cases.
Oh, thank you. And I had another question about the meteorite impact in Greenland. This theory is widely accepted about this one impact in Greenland, but couldn't it been more impacts, like some sort of meteor shower over the glaciated territories?
Probably, maybe, yeah. But about before this meteorite crater, so I got in my hands the manuscript which has been published in Science about this meteorite crater. It was in 2016, if I'm correct. So up to that time, scientists believed that it was huge, let's say, ice meltwater flood into the North Atlantic Ocean. But again, the flood from the melting ice. The way how it melts from the meteorite, it would be abrupt or fast way, but for deglaciation or what we can see today, then the ice melts more gradually up to certain threshold, beyond which it then floods into somewhere. Yeah, and you can imagine what we can see. Let's say it's a movie cartoon, Ice Age. Yeah, the same Ice Age movie, Great Floods. It's basically almost true story about the huge floods in North America. So
Yeah,
it was actually
Lake Missoula, I believe.
Like Lake Agassiz, these kind of huge areas. It was really half of the North America almost was a huge lake. So there might be different scenarios. What our colleagues in Lithuania have been confirming that they have found the impact kind of dust from around that time in Lithuania, which might prove that probably there could be some impact from the meteorite. But again, why not all of them coincide together? Let's say we have meteorite, then we have break of the kind of Laurentidial ice melt waters, then ice melts also from Greenland. So this can be combination of the factors, actually. And unfortunately, we can't go back into a time, as we don't have yet equipment and knowledge about that. But the evidence and science is the best way how we can reconstruct such things. We are like a sort of CIA agents or scientists. So we find certain evidence and then try to understand what this evidence shows. Maybe, Māris, you are correct. Maybe this was a shower, but then we need to look deeper and more for the evidence.
Yeah, but it probably could be a combination of both uniform and catastrophic theories. Sure. Yeah. Thank you very much.
It was nice to hear you.
All right. Thank you for the presentation and for the great questions as well. All right. So we, as the organizers, also have a question we want to ask to all of the lecturers of the series, as the title of the course is Climate Crisis and Climate Action. So both of the speakers could reply to this. And the question is, how should we ourselves approach the climate crisis? And in your expert opinion, what can each and every one of us to do to help solve it? Not sure who of you first could answer this, but perhaps since yeah, you're here. Yeah, Māris, go ahead.
What each of us can do is, well, on one hand, of course, there are some quite simple solutions, and it is energy saving. It is maybe insulation of the buildings where we do live, and other questions. However, the situation and our responsibilities and priorities of the tasks very significantly changed after 24th February. And one of the major sources of greenhouse gas emissions and climate change, of course, is use of fossil fuels. And in this situation, on one hand, we do have the green curse of the Green Deal of European Union, and also political declaration of Latvian government, as well as governments of other EU member states to reduce emission of greenhouse gases. But political position presently is such that many EU member states do have very strict political direction to significantly reduce the use of fossil fuels. And so from state perspective, I think that we have huge progress due to safety concerns, some other factors, and so on. However, another dimension of the same discussion is how we can replace fossil materials to keep some level of welfare, to keep industries functioning, and so on. And so one dimension of these discussions is related to taxonomy, on that what we can consider as green. And as you know, 74% of energy in France is produced using nuclear energy. And there are strong claims supported by France, countries like Hungary, Slovakia, Bulgaria, and some other countries, that nuclear energy is a green energy. And also in our country, presently now are ongoing discussions that we also have to build nuclear reactors. And yes, then we will be yet more green. I'm not quite sure. So actually what we can do, it is a very complex question. There are some elements where each of us, where we can contribute, but maybe more important is our position and our contribution, and maybe support to activities at the governmental level.
Perhaps Normunds, you can answer, and then if anyone else has anything.
Well, I will be short. I don't know. What I got from colleagues from Germany today, that German government really takes seriously to bail out peat consumption, and they claim it's fossil source. So from point of view, they would like also to ease it out from other substances like growing media. So that's not good for our country. So we need to find some solution. So Germany is really strong in this direction, and but that's one option about the energy and production and the shelves of what we can buy on the shelves from the shops. But What we can do, I think we are way over this threshold, and what we need to know now to think is about the adaptation more. And of course, we still need to think about the green energy as such, but it's so abruptly over our heads now, and I think we will not be able to handle this situation quite nicely. So it kind of be messy right now. And I agree there are different ways. I agree with the Professor Kļaviņš that there are different ways. Not sure that they all are green enough, but we are claiming at least that these kind of energies are green. But well, in our best efforts, what we now know is, I mean, we can't do better than we well, our all efforts are based on our knowledge and science, so we can't jump over our capability at this point. We can do our best, but and that's it. I mean, as an individual, of course, we can think all these minor things which you already know, and so I will not repeat them. Walk more and less usage of different kind of energy sources and so on. But I think we are on a way of some climate crisis more than what we are currently seeing. So that's the question, whether you will be capable to live up to 80 years in the same conditions as we are now living here. So yeah, that's kind of troubling my mind, actually, because it will be much faster and more extreme, as already Professor Māris Kļaviņš have been shown in different publications previously. Yeah, so I think we should try our best effort to somehow tackle this issue. I have no solution. Of course, I have no solution. It's just bits by bits, and somehow we need to get to solve this puzzle together.
All right, as some climate activists say, we need to panic. Perhaps that will
always. That helps always.
It doesn't always help. Perhaps, yeah, you have to have a calm mind, but in this case, maybe we need to act faster and thus to panic. And yeah, thank you for your answers. I understand, yeah, that it's of course important to do your own part, but like individual political actions are the basis of what one person can do to ignite the change on a larger scale, basically. All right, thank you to the presenters. If you do not wish to stay for the breakout rooms, you can leave, and the recording of this lecture will be reorganized, so you'll be able to look at it in a calmer manner. Thank you.
Thank you for organizing. I will not stay. Thank you for your time, and have a nice evening.
Yeah,
bye.
thank you.
The same. Thank you, Kristīne, for organizing everything, and it is very good that we have had this discussion. Of course, pity for problems with demonstration, but it always happens, so don't worry.
Thank you. All right.